So to complete our example, we found this eigenvector, or maybe this one, we could use either one, associated with eigenvalue lambda equal to 4. But recall, we've actually found 4, -2, and 1 to be the eigenvalues for the system, but we have not yet found eigenvectors for -2 and 1. So what do? We take our square matrix A, and now we want to say this matrix minus -2 times a 3×3 identity matrix, and then find an eigenvector associated with that, like we did one associated with lambda equal 4. So let's go about that. Okay, this is our solution, and remember this is the general format. So for eigenvalue lambda equal -2, we got 1 minus -2, that would be 1 plus 2, which is 3. And 1 minus -2, again a 3 here, and the -1, they stay. And then we also have 1 minus -2, so we also have a 3 here. So now we'd like to find a non-zero vector that is a solution of this system, or actually the format of any non-zero vector, and that would be the eigenvector associated with lambda equals -2.
Oh, I see.
Okay, so we keep it going on this. Now we have this augmented matrix from this system, and we can solve that. I guess we'll do 1/3 of row 1, and at the same time we can do negative row 2 plus row 3, and that makes a row of zeros at the bottom. 1/3 of row 1 makes a 1 here, a negative 1/3 here, a negative 1/3 there. Of course the 0 remains there. And now that we have this matrix with our nice row of zeros, it would be nice if we had this as a 1. So we'll do 1/3 of that and make that a 1 and that a 1. And then we're going to do 1/3 row 2 add to row 1. So if this is a 1, 1/3 of this add to this 1, 1/3 of this add to this 0, 1/3 of this add to this 0. So golly, here's our augmented matrix now. So what is this saying? This augmented matrix represents this system. And so if we let K3 be arbitrary, this says that K2 plus K3 equals 0, so K2 equals negative of K3, and by the way, our K1 must be 0, because this equation says 1 times K1 equals 0. K1 must be 0, and an eigenvector would be of this form, 0, -1, 1, or it could be 0, 1, -1. Any multiple of this works. So now we've got our eigenvector, this one, for lambda equal 2.
Ooh, this is fun.
Yeah, I'm glad you think so. So let's now find an eigenvector associated with lambda equals 1.
That was very satisfying.
Great, so let's get into that. So 1 minus 1, we're back to a matrix A. That's this one. So 1 minus 1 in the diagonal, 1 minus 1 in the diagonal, 1 minus 1 in the diagonal. Diagonal is going to be all zeros. Other than that, it's going to be the same matrix as what we have there. So here's a diagonal, all zeros, and now we want to solve this system. So the bottom 2 rows say that look, this one says that 3K2 equals 0. Actually, this one says, the second row says 3K3 equals 0, and the third row says that 3K2 equals 0, so therefore the arbitrary value is K1. And K2 and K3 are both 0, so simply we can say eigenvector is 1, 0, 0, or any multiple of that. And now that we have that, we can write the solution of the system.
Mercy.
Yes, so here it is. The solution of the homogeneous system. X is constant times eigenvector that was associated with lambda equal 4 times e to the 4t, plus constant times the eigenvector that was associated with lambda equal -2 times e to the -2t, plus a constant times the eigenvector that was associated with 1 times e to the 1t. So here's another option, by the way. I could, I mean, this C1 could be 3 times what this C1 is, or negative 3 times what this C1 is, in which case it looks like this. This one could be a 1 here and a negative 1 there, right, because it's just another multiple of that. This one, well, not much I can change about this one. I could call that a 10 if I wanted to. It would just alter the value of our C3. So with our arbitrary constants, we have actually solved the case where we have repeated eigenvalues, and each of our eigenvalues we could, sorry, not repeated eigenvalues, distinct eigenvalues, and each of our eigenvalues we constructed a matrix, and that's that.
Will this unit always be this complicated?
Yeah, it doesn't get much better.